Just leave that off. Steady green light, that's good, right? Yeah. 3 requirements for a model to generally have a good chance of being successful in forecasting. And the first one is that the model has to link well past data, that is the data that we're going to use to estimate the model's parameters, before we then, with that estimated model, forecast beyond those data, that model links the data that have been used for estimation, the past data, in a sensible, systematic form to the data in the out-of-sample period for which we are forecasting. And we will see that these AR models, at least under many parameterizations, are going to be so-called stationary models. And they're going to satisfy, in terms of properties for the unconditional second moments of the data, then a feature that is shared across all time periods. And so if core features, and we will see that's going to be time invariance of the unconditional second moments, is shared by the past data and the future data, then you should have, right, a good chance that the model actually can forecast reasonably well. If there's some future regime that had nothing to do with the past, could I hope that on the basis of a model estimated with past data I could forecast well? No, right? I mean, if the future is just unrelated to the past, maybe go to fortune tellers again. Right? That's then as good a bet as anything else. So we have to have that there is a relationship between the past data, how the dynamics are unfolding during that past, with the future. And if basically our models, and we'll formalize that, are in that class of stationary models, then we have good reason to believe that the past data have a good bit to share with the future. We'll still work on other kind of regimes too, but that's going to be one possibility, right? That the past and the future share a lot in common, systematically share a lot in common. The second criterion for a model to do forecasting well is that it's parsimonious. That is, that there's relatively few parameters in the model. Why? If you had lots and lots of parameters, the risk is that these parameters are going to be estimated subject to sample specificities, right? If you have relatively few parameters in the model, you might think these parameters are basically going to be set in such a way that the main features of the dynamics are reflected well. Whereas if you had a model that had lots and lots of parameters, you go after every nitty-gritty detail. And that may not be helpful, because these nitty-gritty details may not show up in the out-of-sample period, right? Even with the out-of-sample period in a broad sense, share a lot in common, these observations in the out-of-sample period. With the past data, they'll not share every nitty-gritty detail with the past data. And so from that perspective, better work with a model that focuses on the essentials. And that will typically be a model that has fewer parameters, that is relatively parsimonious. And then the third thing, of course, the model has to be analytically tractable, so that we can do the estimation, calculate forecasts for the model, and we'll see for the AR models that's going to be particularly strongly the case, that they're going to be analytically tractable. So we'll visit now such AR models, but again, this is part of the course where you shouldn't search for how did economic theory motivate this model, because that's not the case. This is a purely stochastic process that's popular in time series modeling in general, but that also turns out to be useful for forecasting in macroeconomics. And so we will probably within the course, but in general, certainly see situations where these models despite the fact that they're not motivated by economic theory, despite the fact that they don't have lots of bells and whistles, still do the best in forecasting compared to other models. And again, then we'll revisit the reasons. But when thinking about that later on, how well a model does do in forecasting, always think back to these 3 points emphasized here at the beginning, that the model has to make successfully a link between past data and the future. The model has to be parsimonious, focusing on the key aspects of what is present in the past data as well as in the future that we try to forecast. And the model has to be tractable, so that we can do the estimation successfully, calculate the right kind of forecasts, and so forth. Okay, now where to start? Let me first remind you of this principle of stationarity. That's for us, for much, not all, but for much of forecasting, going to be the key link between the past data and the future data, in the sense that when stationarity does hold for a series in sample, out of sample, they share quite some common characteristics. Namely, they share an invariant mean, unconditional first moment of the series E, our unconditional expectations operator of the series Y at time t, here denoted to be constant, right? That says in any given period, we expect the series to have the same expected value. First form of time invariance. And the second form of time invariance for a stationary series is that the covariance between the series Y at time t and Y at any other point in time t minus L, in that L could be any integer value, 0, plus minus 1, plus minus 2, and so forth. The covariance between yt and yt minus L for any L is just a function of L. Right, imagine L was 1. Then we measure the covariance between yt and yt minus 1, the covariance 1 period apart between yt and the value of y 1 period ago. If that is the same over time, it means, for example, for annual data, that the covariance between the series in 2020 and 2019 was the same as between, if that series went into the future as well, 2026 and 2025. Right? And so it, of course, would help us a lot, because that historical measure of dependence 1 period apart will hold out of sample in the forecasting period as well. And of course, not just 1 period apart, right? Again, you can plug in LEL, 2 periods apart, 3 periods apart, not just looking into the past, but for those negative values of L going into the future as well. Right? And so this is beyond the fact that the mean of the series is constant, also an invariance property in terms of strengths of the relation across time periods. Stationarity says the strengths of the relationship across time periods so it only depends on how many periods apart do we observe the series, right? Of course, 1 period apart for L is equal to 1. The measure of dependence could be very different than, say, for L is equal to 4. We could have a stronger form of dependence 1 period apart, L is equal to 1, then for 2 periods apart, then for 3 periods apart, 4 periods apart, and so forth. But if it's the same number of periods apart for which we measure this dependence, then it's not changing. Excuse me. Okay, should be better now. So the point is, key patterns of how the series can be characterized in terms of first, second moments are time invariant. The mean is constant across time. The covariance across different time periods, sometimes we also call that the autocovariance, right? Because it's the covariance of yt with itself in a different time period. The autocovariances depend only on the displacement in time, that is L, right? How many periods apart do we measure that strength of dependence? Of course, there's other moments, right? You could say, what about the third moment, the fourth moment? Somewhere in the back of your mind, you remember we heard about skewness, kurtosis, and so on. This is not saying that it's the same distribution across all periods. That would be a much stronger notion. So-called strict stationarity would actually say the whole distribution is the same each and every period. This is not what stationarity, or sometimes also called weak stationarity, does talk about. It only talks about invariance of the unconditional first and second moment, right? The mean, of course, for L is equal to 0. The special case of this is the variance, so the variance also is time invariant, plus the autocovariances in time. All that is time invariant, and so there's a good bit of invariant structure that stays unchanged over time, and that gives us a chance that if a process does satisfy this requirement, we could actually have some hope that we're going to forecast right. Now, maybe one objection you'd have here immediately is that you'd say, but for many economic series, it won't have a constant mean. Right? If, for example, I was to plot data for GDP, say GDP on a per person basis over time, then of course we'd hope that GDP is not having a constant mean, but that it can grow upwards, right? I mean, that's, I guess, the first thing I'd hear somebody asking me about in Vietnam when I say, I'm in macroeconomics. So what's going to be growth for Vietnam? Now, is our target 4 or 5%? Is it realistic, right? And of course, GDP growth means, therefore, that the series goes upward. And we already know from macroeconomics it doesn't go up like a straight line, but there are business cycles. There's periods of expansions, there's periods of recessions, so it goes up a bit in cycles. Now, of course, from that perspective, given that it's going up, you can have a constant mean. Right? So clearly GDP per capita cannot be a stationary series. So do we already rule out at this point some of the most interesting series? No, because often there will be very simple transformations to render the series that per se doesn't have a constant mean into a series that does have a constant mean. Well, if I measure the deviations of GDP from this trend line, then the way I have plotted it, at least it seems not impossible at all. I did have average across all those deviations that they average to 0. That is that this detrended GDP would have a constant mean, in this case perhaps even a mean of 0. Right, so there's going to be simple transformations for many series that will mean that you don't have to think, well, this is all nice and good in theory, but not practically useful if we assume at the outset that the series has a constant mean. There may be some series that do have a constant mean, but even if it doesn't, a simple transformation often will have a constant mean. So I think that's less of a problem often in terms of violation of stationarity. The second one is going to be a bigger issue, and we'll come back to that specifically when we'll talk about these unit root models Riemann models, one prime example where those variances are not time invariant. And that's going to be a little bit of a harder fix than trying to fix a non-constant mean. So in terms of the stationarity restriction, two messages I'm trying to convey. Don't think it's that hopeless. Right? If you said, well, that's totally hopeless, because if I just thought, say, about GDP per capita, maybe the most important series of all in macroeconomics, it's never going to have a constant mean. That's a proper argument, but the argument against it is we can find simple transformations to transform it into a series that has a constant mean. So the bigger bite in terms of practical restriction on whether the series is stationary or not is going to be this time invariant covariance structure assumption. We'll initially presume that it holds. We'll see what restriction that's going to put on AR models, but then again, we'll also relax it later and see how we can still model and forecast well in situations where that second assumption is broken and cannot be that easily fixed. All right. Now, one reason why I mentioned stationarity also right at the beginning is because there is a very powerful theorem in time-series econometrics, the so-called Wold decomposition theorem, that tells us if we restrict attention to stationary in the form of the previous slide, weakly stationary, time invariant first and second moment. If we restrict attention to such models, we can give them an algebraic representation. For any type of weakly stationary model, it is true that beyond some deterministic model components that are here reflected for YT through this tau, could be, for example, some seasonality. If some sales had a seasonal component, right? That certain products are sold in a seasonal variation type of form, that maybe mooncake is more popular during the fall festival, and that some other goods are much more popular during Tet, but not so popular maybe in the month of June or July. That's not stochastic variation, right? That's deterministic variation that we can anticipate on the basis of people's behavior around holidays, for example, right? Let's take that out, right? The model in equation 1 just says the tau represents the linear deterministic component. Let's take it out. Let's forget about that. You could also think of it, right, that we are writing YT minus tau, so that this tau, this linear deterministic component, has been removed. And then we focus what's left on the right-hand side. What's left on the right-hand side to generate any weakly stationary series? A semi-infinite sum, j equals 0 to infinity, of parameters that satisfy some regularity conditions. I'll talk about that in a second, but for now just think of those as parameters, times IID shocks. Epsilon t is IID, that means 0, variance sigma squared, kind of the shock in the linear regression model. And so what equation 1 says is, if I take a weighted average of current and past shocks, weighted in the form of these parameters psi j, I can generate any weakly stationary series. And we will not prove this, of course. This is beyond the scope of this course, not our interest. And it's a very powerful statement because it says, if I am willing to restrict my attention to weakly stationary series, I know how to construct them, and they're actually linear models. They are linear functions of current and past shocks. I don't have complex nonlinearities or anything to worry about. Just do a linear combination of current, epsilon t, and past, epsilon t minus 1, epsilon t minus 2, epsilon t minus 3, and so on, shocks, I can generate, except for this linear deterministic component, any weakly stationary series. That's what makes this Wold decomposition theorem so powerful, right? If you think back one slide, where they said, okay, fine, I mean, I can understand that the stationarity is a sensible restriction in the sense that it helps me to link past data to out-of-sample future data. If they have all these common set of characteristics, it's well imaginable that the past data help me understand forecast future data. That's fine, but what's not so obvious from the stationarity requirement is which models to work with. How can we make sure that we haven't forgotten some interesting stationary models, right? And that's where the Wold decomposition theorem comes in and says, well, actually all that you need to do is, beyond this linear deterministic component, is to find current and past shocks with appropriate weights, psi j, can generate any weakly stationary series. What are the restrictions on these weights? That's just a normalization right on the current shock, that the weight on the current shock is 1. That has to do with identification, in particular also of the variance of the process, but it's just a normalization, don't worry about it. And the second restriction on the semi-infinite sum of the squares of these parameters on the shocks is a finiteness restriction, right? It says that this must be bounded, cannot be unbounded, is finite.